inscribed angles within circles. So we'll start with just a basic definition of what congruent circles are and go from there. So we say congruent circles can be described as circles that have the same radius length. So typically when we say that things are congruent, it means that they're the same size. In terms of a circle, we really say, hey, the radius length is the same size. We could also put in there they have the same area, that they have the same diameter, they have the same circumference. But to keep it simple, we just say the same radius length. So a follow-up question is, if we have two circles, O and P, and we say that they're congruent, what else can we say? So the first thing that we can say is that they have the same radius length. We just said that. The other thing is that they can be mapped onto each other using rigid motions. So if you recall, rigid motions are your transformations in which size is kept the same or maintained, and that means that we have reflections, translations, and rotations. So O and P, those circles, are congruent if they can be mapped on to each other using rigid motions. Then they would have the same radius length and everything else would fall into place. Now, are all circles similar? And I know on your paper you have some circles, and I just want you to think about that for a second. Are all circles similar? And hopefully you're saying yes. And if I ask you to explain why, I'm thinking you are on the thought of, well, they're all circular, they're all rounded, and all accurate, yes. But in our class in geometry, what we say is that all circles are similar for the mere fact that they could all be mapped onto one another using similarity transformations. So we're changing it from rigid motions to similarity transformations because we have to include a dilation. Now, think about it. If I take this circle and I translate it, and then I shrink it or I dilate it to make it smaller, they would be similar. If I take this circle and I translate it, and then I dilate it to make it larger, then it would map onto the circle here. So all circles are definitely similar because similarity transformations work from one to the other. Okay. All right, moving on. It says, can you name a series of similarity transformations that map circle A onto circle B? So here's our pre-image at circle A, and circle B is where we end up, so that's our image. And here it is. So how would we get from A to B? And kind of walk us through it. First thing is, I'm thinking if I take A, the center point, and I translate it along this vector B, now that means this entire circle is up here at B. Okay, so the first thing we need to do is we need to translate. Usually when you translate, you give a direction in terms of maybe 4 right and 3 up, or so on and so forth. We don't have that flexibility here because there is no grid. So we say we're going to translate along this vector AB, and then we need to make it larger, and we need to dilate. And remember, when we dilate with a scale factor. So our scale factor here is image over pre-image. So take a look at what we have. We're going to dilate with a scale factor, and then we're going to translate along the vector. So if we're going to do this totally, we have this here. Oops. Extend my page. Our translation is along this vector AB. Our dilation is over here at the circle B, and it's image over pre-image. So it's R2, this radius, over R1, that radius, right? It's the radius of the image over the radius of the pre-image. Remember, we don't have any numbers to say, hey, dilate this by a scale factor of 2 or 3 or 2.5, right? We don't have those values. So we simply say whatever this radius length is over that radius length would give us the scale factor. And this is an example of how we translate, then dilate to perform some similarity transformations. Okay, so now the good stuff. So anytime we have circles, we can create some different types of angles. So the first angle that we can create is called a central angle. So a central angle is an angle whose vertex is on the center of the circle. So the vertex essentially is the center of the circle. So if you were to highlight angle A O, B, and you take a look, O is the center of the circle. If I were to highlight angle D, O, C, O is the center of the circle. So angle DOC or COD are both central angles. Okay? The reason why it's important to notice that they're the center is because since it's a central angle, there's going to be an important relationship in terms of the angle measure. Let's take a look. Here. If angle AOB is 90 degrees, what do you think the measure of arc AB, so from here to here, is in terms of degrees? Now notice arc AB can also be represented by the symbol up here. Put a little arc over AB, interchangeable. So if you have any guesses, if this is 90, what this is up here? And we're just going to say, all right, well, if this is 90, this looks like it's a quarter of a circle, right? A quarter of a circle, well, a quarter of 360 is 90. So yeah, so that arc length is 90 degrees. So up here, this is 90. Perfect. All right, so do you see a relationship? Yeah, this is 90 and so is this. And the relationship is, well, with central angles, the measure of the arc is equal to the measure of the central angle of the arc that intercepts. So here we have the degree measure of an arc is equal to the measure of the central angle that intercepts the arc. So if you know the angle, you know the arc that it intercepts. So if you look here, let me say intercepts, if I kind of highlight this AOB, almost think of it as like a Pac-Man. It eats up this angle, so this is the arc that it intercepts based on this angle. All right, so here are just some examples of how we use the central angle with the angle arc relationship. So here, AOB is the diameter. It goes through the center of the circle from side to side. So we don't even have to be given any information. We just know that the diameter divides the circle in half. And a full circle is 360, so half of 360 is 180. So it works here as well as here. So 180 for angle AOB, 180 for arc AB. Then over here, it's giving you that arc AB is 130. So notice I put like a little arrow. Since this is my arc, the central angle is 130. So angle AOB is 130. Now, here's the interesting part. Over here, if I said angle AOB, there's two angles. There's an angle up here and an angle up here, but both angles are at 180. So if I said angle AOB is 180, no matter what angle I'm talking about, I'm correct. But here, if I say angle AOB, I could also talk about angle AOB going this way. And that's definitely not 130. That's larger than 130. That's 230 because it's 360 minus 130. So we introduced minor and major, and we talked about this in previous lessons. So a minor angle is going to be an angle that's less than 180. A major angle is one that's going to be greater than 180. We could also we really talk about minor and major arcs, but in terms of angles, it also applies. So down here, we just kind of have those definitions for minor, major arc, and we show it in terms of here, if this arc, AB, is 90 degrees, that's going to be my minor arc because it's less than 180. And then you have an option. If I'm talking about this arc, this major arc, I can either say major arc, AB, and say that's 270, or notice I just put another vertex here, another point, C. And I have ACB, and now when I say arc ACB, you go in that order. So from A to C to B, bam, is 270. Okay, and you can see this is greater than 180, this is less than 180. Okay. So here's an example. And my work is here so we can kind of walk through this. So it says, given circle O, we have to find the measure of angle AOB. So here's AOB. AOB. Now let's just talk about what they gave us. They gave us that this arc is 160. So from B to C is 160. So that means if I form the angle with that arc, angle BOC is also 160. All right. They also tell us up here that this angle is 90, right? Oops. Since it's a central angle, if I follow it out, the arc that it intercepts out here is also 90. Perfect. And then I use the idea that a whole circle adds to 360. So I add 90 and 160, gives me 250. Subtract that from 360 and I get 110. So the piece that's left over here is 110. That means that this arc is also 110. And then just go down the list. Okay, so angle AOB, 110. Arc AB, and I didn't really kind of tell you minor or major, so I just put minor. Minor arc AB is also 110. And then arc ABC, and notice I don't have to say major or minor because there's 3 points that have to go in that way. So A to B to C means they have to add 160 and 110 to give us 270. Okay. That's how you kind of work with the central angle, arc angle relationship there. All right. So let's see here what we have. We have to find the values of x and y. Those are arc values. And for this, I really like to focus on that they gave us a diameter. So here it is. So here's your diameter. They tell you that this angle AOD is 120. That means that this angle here is 60. And the reason why is since AOC is the diameter, it splits the circle in half. This whole arc or this whole angle is 180. So that means that this is 60. Now, since this is a central angle, COD, that means that the angle, the arc that it intercepts is the same. So it's also 60. All right. So I found X, that's 60. Now on the other side, similar, right? If this is 50 BC, I can look here. That's the angle. So the angle is also 50. Perfect. Well, if this is 50, it has to be 180, so 130. And then if this is my central angle, I go out, and there's your 130 also. So 130. Okay, so X is 60 and Y is 130. Hope the central angle idea is getting a little easier for you. I know we just learned about it, but if you really see that the central angle is the angle formed at the center, the angle and the arc that it intercepts is equal. All right. So the next kind of angle we're going to talk about are called inscribed angles. So an inscribed angle is a little different because now the center or the vertex is on the circle. So look at angle ABC. B is no longer the center, it's actually on the circle. So that's known as an inscribed angle. So really I could place any point on a circle. Let's do this. And say, okay, this is it. I'm going to go from here to here, here to all the way over here. That's also an inscribed angle because the vertex is on the circle. So when you name the angle, it's really in terms of where the center of the angle or the vertex of the angle is located. So the next page, look at an example. So it says here, what do you think the measure of angle ACB is? Okay, so here's the thing. We know angle AOB is 90. Okay, so if we know that this is 90, we want this angle here. Now, if we know that this is 90, we also know that this arc from A to B is also 90 because this is a central angle. Now, this is definitely an inscribed angle. And if I'm looking here, this angle does not look 90 degrees. It looks less than 90. Can you take a guess at how many degrees you think that angle is? And usually, a lot of students guess like 30, which isn't bad. It's actually 45. And maybe you guessed 45. Now, we have a relationship. This is 90, this is 45. The angle is half of the arc that it intercepts. The angle is also half of the central angle that it kind of intercepts as well. All right, so when we're dealing with inscribed angles, the measure of an inscribed angle is half the measure of the arc it intercepts, whereas the central angle is equal to the inscribed angle is half of. All right, so let's look down here, and here are just some example questions. Pretty straightforward. So here's your arc at 60. I take a look at my angle, highlight it. Oh, it intercepts that arc, so it's going to be half of 60, which is 30. Makes sense. Now here, the angle is 50. I have to find the arc. Well, if I knew the arc and I took half to get the angle, if I want to find the arc now, I have to multiply it by 2. And think about it. It's the 50, the angle is equal to half the arc. So I have to multiply this by 2 to get the arc. So the arc is 100 there. Okay, it's working with inscribed angles. So if you take a look at this picture, it says, how does this diagram illustrate the inscribed angle theorem? Now, this really goes back to a lot of kind of including a lot of different thoughts here. So first, how did I get all these numbers? So for angle B, I ended up with 30 because I know that angle B intercepts arc AC, here to here. This is an inscribed angle since it's on the circle. So 30 I have is half of 60. Perfect. Angle A intercepts arc CB here at 150. So half of 150 is 75. And then finally, angle C intercepts arc AB. So half of 150 again is 75. Now, two things I know here. This triangle, my degrees, my angles, are 75, 75, and 30, which is 150 and 30 is 180. We know in a triangle, all of the angle measures have to sum to 180. Outside the circle is 150, 150, and 60, so it's 360. So, not only is each angle in the triangle half its intercepted arc, the total sum of the angles in the triangle is inscribed inside of a circle. The circle is 360 and the angle is summed to 180. There again is that whole half relationship. So, each angle is half the intercepted arc, true, and the circle sums to 360 while the inscribed triangle sums to 180. 180 is half of 360, right? So since this triangle is inscribed, it's half of the circle, which is 180. That's kind of how it shows it there, just using that inscribed angle theorem. Okay, and we have one last page to go through. And these are just a couple of questions that have come from previous Regents exams. So this one says, on the diagram below, DC, AC, DOB, CB, and AB are chords of circle O. FDE is a tangent at point D, and the radius OA is drawn. It should say Sam, decides to apply this theorem to the diagram. An angle inscribed in a semicircle is a right angle. Okay, so first we're looking at an inscribed angle, and it has to be in a semicircle. So semicircles mean we have to deal with the diameter. Semicircle is half a circle, diameter. So the only diameter I see is DOB. So I need an angle that's inscribed that includes points D and B. So really, kind of by process of elimination, if it's inscribed, it has to include C or A, right? Because inscribed angles, the center must be, or the vertex must be on the circle. So if I have to include D and B, A goes to B, but doesn't go to D, so that's not good. But over here, C can go to D, and C goes to B, right along these little chords. So the angle I would have would be DCB. That would be this inscribed angle. Now this angle is actually a right angle because it's half of the arc, which is 180. All right, so let's see if we can find angle DCB. AOB, we said no. BAC, also no, right? These two are incorrect because if it's AOB, that's a central angle. BAC is an inscribed angle, but this here is in a semicircle. Oh, and here it is, DCB, trace 3. So DCB. So this is an angle inscribed in the semicircle, which would give us a right angle. All right, and then this here, which this question is very helpful because we kind of come up with an idea based off of this question. So we have to find the measure of angle BCD here. So if A is 110, we know from D all the way to B, this is 110, it's inscribed. That means that its arc has to be 220. Okay, so that's from D all the way to B. That's a major arc. I could also find this minor arc, right? If the major arc is 220, subtracted from 360, my minor arc is 140. That means that this angle, C, inscribes that minor arc. So angle C is half of 140, which is 70. And that would be your answer then. Angle BCD is 70, half of 140. Now here's the thing. The relationship that forms is that if a quadrilateral is inscribed inside of a circle, so you have any four-sided shape inscribed in the circle, the angles that are opposite each other, so these two angles are opposite, are going to be supplementary. Okay. So you have 70 and 110, they add to 180. This is 72, this means that this angle over here would be 102. They would be supplementary. Okay. So that idea of opposite angles in an inscribed quadrilateral of a circle or supplementary is huge and really going to help you out. Okay? And I actually think that is it. So some major takeaways that you should be kind of even jotting down just for yourself is definitely what we just discussed, that in a quadrilateral that's inscribed inside of a circle, opposite angles are supplementary, super helpful. The other thing that you want to take away is about the inscribed angles are half the measure of the intercepted arcs, right? Huge. Inscribed is on the circle. It's half the measure of the arc. And we also said for the central angles, the arc is equal to the measure, I should say that the arc and the angle are equal. Right? So if you know the measure of the angle, it's the same for the measure of the arc that it intercepts. If you know the measure of the intercepted arc, you know the measure of the angle. Remember, a central angle is on the center of a circle. So vertex is the center of the circle. Central is same. Central, center, same. That's how I remember it. Okay. And then we also just discussed ways to describe congruent circles as having the same radius length, right? And saying that all circles are definitely similar, and we're able to use similarity transformations to describe how one maps onto the other. So that really ties up the intro to circles lessons in terms of just describing similarity transformations, central angles, inscribed angles, and also on the final page here, just talking about having an inscribed quadrilateral. There is no lesson, nothing to submit with this lesson. On Thursday, you will have a castle learning practice that includes some of the ideas from this lesson. So if you have any questions, please feel free to, you can kind of message me within the Google Classroom, or still feel free to email me. Okay.